All right, today we're going to expand upon our knowledge of exponential functions and start talking about exponential growth and decay. So I want you to think about, do I remember the form for an exponential function? Can you do it before I remind you? It was y equals a times b to the x. Okay, we are going to be focusing still on this formula. Okay, but I want you to think about, how do you think the value of a impacts the function? What do you think that does to it? And then how do you think the value of b impacts the function? What do you think that does to it? Okay, so if I had let me give you an example, like y equals 4 times 2 to the x. I hope you could tell me that this function would start with 4, and then it would multiply by 2 every time. Okay, so it looks like a, that's going to be your starting amount, okay, or your initial amount, and the value of b, that's going to be your constant ratio, the number that you multiply by each time. Okay, so I want you to think about this. What has to happen for your function to continually increase? Do you care about the starting amount or the constant ratio if you want it to increase? If you notice that you care about your constant ratio, think about what you might have to multiply it by. Would any positive number work? How about like a half? Oh, not a half. That wouldn't work. It would not. That would make it decrease. How about 1? 1, that would make it stay the same. If you want your function to continually increase, b has to be greater than 1. The number that you have to multiply by every time has to be bigger than 1. If you want it to decrease every time, then b has to be less than 1. But b has to be greater than 0. Because otherwise, if you have a negative value, remember it will go positive, negative. So sometimes it would be increasing, sometimes decreasing. So to increase, you want b to be greater than 1. If you want it to decrease, b needs to be less than 1 but bigger than 0. Okay, so here's this form. Everything that's exponential growth or decay will still have that form, y equals a times b to the x. And I'm going to show you a very wordy slide. And if you are the type of person that likes to write every little detail down, you can write this very wordy slide, or we can just talk about it. I tried to simplify it. Exponential growth, that's going to be when something keeps getting bigger and bigger and bigger. Okay, it could be modeled with this function again, y equals a times b to the x, where a is the starting amount, and b has to be greater than 1 to get it to keep growing all the time, and that number is called the growth factor. Okay, it's our constant ratio, but it's our growth factor, the number that we keep multiplying by every time. If we're talking about exponential decay, it's in the exact same form. Y equals a times b to the x. A is still the starting amount, b is still the base, but this time it's between 0 and 1. Okay, so bigger than 0, less than 1. And then we call it the decay factor because it keeps making our numbers smaller and smaller every time. Okay, so let's look at some problems and see what we can figure out. All right, in 1998, a certain town had a population of about 13,000 people. Since 1998, the population has increased by about 2% a year. So if I was looking at a problem like this, I would know it would be starting at 13,000 people. And then to find out if I'm increasing by 2% a year, this is important. I still have my old 100%, but now I have 2 more percent. So my value is going to be 102% of what it used to be, okay, of what it was. That's going to be an important concept. So when I have this number 13,000, to find out how big it will be the next year, I would multiply it by 1.02. And if I wanted to figure out what it's going to be the year after that, I'd multiply that answer by 1.02, etc., etc., etc. So it looks like a good equation might be y, if y means my population, equals 13,000, my starting amount, times 1.02, which in this case is my growth factor, to the x. If y was my population, as I said, and x is the number of years after 1998, I'll say, because that's what we had last time. Okay. All right, so now what you're going to do is use your equation to find that approximate population in 2006. So we had that y equals 13,000 times 1.02 to the x. And we knew that x, let me look back at it, but it was the years after 1998. So 2006, that's 8 years after 1998. So we're going to do 13,000 times 1.02 to the 8th to figure out y. So I'll show you how to do this just on a calculator. You probably already know, but just in case. I definitely need a calculator for it. So we're going to, I'll pull that screen out. So we're just going to do 13,000. Okay, and then times. And then you'll want to do 1.02 and then use the caret to the 8th. Okay. We get an answer like this, 15,231.57, and obviously we're talking about people, so we want to round. I'm going to round it to the closest value, which is 15,232. So we're going to get about 15,232 people is going to be our population at this stage. Okay. So a pretty significant growth in just those 8 years. All right, let's try another one. This is very important. Okay, suppose you deposit $1,000 in a college fund that pays 7.2% interest compounded annually. Find the account balance after 5 years. So if we're thinking about this again, you get 7.2% of the interest that you had before. So you'd start out with that $1,000, okay, and you already have the 100% of it. Plus now you get 7.2% more. So we have 107.2% of what we had last time. So we'd be multiplying by 1.072. Okay, and if we're going to keep that in there 5 years, we do that to the 5th power. So my amount should be 1,000 times 1.072 to the 5th. So this time I'll just do it on my normal calculator. And I'm going to see that I'm going, this time I don't need to round it to the nearest whole. I can round it to the nearest decimal of cents. So I'm going to get $1,415.71. Okay, so that's nice. All you did is let it sit in there, and after 5 years, you already had $415.71 more. You didn't have to do anything more to earn that. Okay, so it's nice. Investing, obviously, your parents probably tell you that pays off. All right, this is a note. This is kind of tricky. Annually means per year. If you get a 4.8% annual interest rate, you won't get like the full 4.8% per month or per anything. That's what you get per the year. So if I asked you your quarterly interest rate, quarterly means 4 times a year, and I asked you to figure out what it was, do you have a thought of what you would do? I'm not sure if you know it, but what you would do is you would do 4.8 divided by 4, and you would get 1.2% quarterly. So if they were going to make you just get interest quarterly, you'd get 1.2% every quarter. If you were getting a monthly interest rate, then this time we would do 4.8 divided by 12, and this time we would get 0.4% monthly. Okay, this will come in handy when we're working on problems with bank accounts or whatever, when they're compounding interest at different amounts of time. So let's look at this one. So suppose the account in the above problem, and I rewrote it here, you were getting $1,000 at 7.2% annual interest rate. Suppose it paid interest compounded quarterly instead of annually. Find the account balance after 5 years. So the first thing we need to do is 7.2 divided by 4, because that's going to give us the amount of interest we make quarterly, and that's 1.8% every quarter. Okay. And what's going to happen here? So remember, I already had 100%. I'm getting another 1.8%, so I'm getting 101.8% of the amount I had. So when I start with $1,000, I'm going to multiply it by 1.018. But this time, when it's after 5 years, I have to say, how many quarters is that? So remember, there's 4 quarters in a year, so that's after 20 quarters. So this time, instead of taking it to the 5th power, I'm going to be multiplying by 1.018 20 times. Okay, so we're going to see if that makes much of a difference for us. Often it just makes a slight difference, but it looks like at this stage, if this is y, my amount of money, and I fill out that equation, I get $1,428.75. So if I compare that to the earlier slide where I got $1,415.71, I would rather have them compound it quarterly because I'm going to make about $13 more. Okay, so the more often they refresh your interest rate, the better, because then you keep getting paid more on the interest. All right, so here we go. Technetium-99 has a half-life of 6 hours. That means if it had, you know, a certain amount of technetium-99, say it had 100 grams or whatever, after 6 hours it would have half of its amount left. It would have 50 grams, and then 6 more hours it would go to 25. Okay, so suppose the lab has 80 milligrams of technetium-99. I want to know how much technetium-99 is left after 24 hours. So you could probably logic this one out with a chart, but I still want you to get in the practice of making an equation. So we're going to start at 80 milligrams. And then every 6 hours, I'm going to multiply it by half of it, by 0.5. If I'm looking for 24 hours, I would do 24 divided by 6, which is 4. So the 0.5 would get raised to the 4th power because I multiplied by 0.5 4 times. So if I do this, 80 times 0.5 to the 4th, I get an answer of 5. So after 24 hours, that 80 milligrams of technetium-99 that they started out with, we're down to 5 milligrams. Okay. All right. This time, instead of being 50%, this is where it gets a little trickier. Suppose the population of a certain endangered species has decreased by 2.4% each year. And suppose there were 60 of these animals in a given area in 1999. What you're going to try to do is write an equation that models how many animals are left. So here's important. You start out with 100%. But we're not multiplying by 2.4% every year. We're losing 2.4% of the population every year. So like before where we added it, this time we're going to subtract. So it looks like we have 97.6% of the population left. And that's what we care about because that's what we can continually multiply by. So we're going to start with 60, and then it looks like I'm going to be multiplying by 0.976, okay, to the exponent. Okay, we'll call it to the x power. X is going to represent years after 99, after 1999, and Y would be my population, my animal population. Okay, so this is kind of a key importance. A lot of people, when I've taught them in the past, they want to just multiply. They're like, oh, it's decaying. I'm just multiplying by 2.4% every year, but that's not true because you have to see what you have left, okay? So you have to multiply by 100% minus that amount. All right, if I ask you to solve this, use your equation to find the approximate number of animals remaining in 2005. So it was y equals 60 times 0.976 to the x, and x was the years after 1999. So in this case, 2005 minus 1999, we have 6 years afterwards. So we're taking that to the 6th power. So I'm doing 0.976 to the 6th, and then I'm going to multiply that by 60, and I get about 51.86. But obviously it's a number of animals, so I'm going to round. I'm going to say it's probably about 52 animals that are left in 2005. Okay, so that's exponential growth and decay in a nutshell. And we'll practice a little bit more until you get pretty good at this concept.